Chapter 19 is basically on using the ideal gas law. Now, we'll prove the ideal gas law later, but really it's a very sensible thing. The ideal gas law says basically there are three different ways to change the pressure of a gas. Now, remember that pressure is the bombardment of the molecules of the gas. It's actually the force per area from the bombardment of the molecules. So like we see the molecules hitting the walls of the container, the pressure has to do with how often they collide with the wall. Basically, you could measure it as the number of collisions per second. So we'll think of pressure that way. And how could I increase the pressure? There are like three ways. One way is if I just put more gas particles in there, more bombardment on the walls then and greater pressure. So we expect that pressure should be proportional to the number of particles. The second ingredient of the ideal gas law is that you could make the bombardment stronger if you increase the temperature of the gas. In other words, if the gas particles are moving faster and they have higher energies and therefore temperature, that will increase the pressure as well. So we've got the two ingredients. You can increase the number of particles, or you can increase their energies. Both of those will increase the pressure of the gas. Finally, if I shrink the container, if I put the same particles moving at the same speed, but in a smaller space, they will hit the walls more often. Think of crowding people into a tiny room versus an auditorium. They're going to bounce around more frequently. And that means that decreasing the volume should go along with an increase in the pressure. The ideal gas law simply states those relationships, that pressure is inversely proportional to the volume, or in other words, pressure times volume is equal to some constant. The pressure is proportional to the number of particles, the number of moles of particles, and then it's also proportional to the temperature of the gas. So those are the three ways to change the pressure. Now I want to remind you that whenever you work with the ideal gas law, you'd better be working on the Kelvin scale of temperature. Everything sounds hot on the Kelvin scale because it's measured from the absolute zero of temperature. So if you want to know the value of T in the gas law is given in Kelvin, you have to take the Celsius temperature and you've got to add 273.15 onto it. Okay, so whenever we use ideal gas law, it must be on the Kelvin scale of temperature. 0 Kelvin, for example, being meaning the particles have no energy, they don't move, and they don't bombard anything. So there'd be no pressure. Okay, and as you know from using the gas law before, probably in a chemistry class, the value of R is a universal constant for these gases. The value of R depends on what units you're using to measure the pressure and the volume. For example, if you use atmospheres and liters for pressure and volume, then the value of R is 0.08214, this one here. However, if you use standard metric SI units of pressure and volume, then you use a different constant. There's a conversion factor that's needed, and you measure it with a value of 8.314. I want you to notice one thing, which is that pressure times volume actually has units of joules. That fact will help us later. So I want to just show that for a second. Pressure is measured as newtons per square meter. That's pressure. Pascals for short. Okay, so pressure is in pascals, that's force per area, multiplied by units of volume, that's meters cubed. Okay, that's how you use the gas law, multiplying pressure times the volume of the container. And notice that meters cubed divided by meters squared is meters. So overall, the units of the left side here come out to be newtons multiplied by meters. And we all know that force times distance is what you call work and has units of joules. So that's why the gas constant, in standard metric units, the units for it are joules divided by moles kelvins. Now, I want to be clear that pressure times volume is not the energy of the gas. All I'm saying is it has the units of energy. We'll figure out later how to do things with energy of gas. Okay, this is the standard way it's written in that you've seen it before in terms of the number of moles of gas. Sometimes, however, so chemists count by the number of moles. If a chemist says there are 2 of them in the container, they mean there are 2 moles of gas, which is, many trillions of molecules. However, if a physicist says there are 30 of them in there, they mean there are 30 particles in the container. We're actually counting the number of them. So we'll sometimes use the ideal gas law in a slightly different form, the physicist version of it. In the physicist version, I'm actually, I don't want the number of moles, I want to convert to the actual number of particles, and that's easy. I just have to make a replacement. Number of moles means I take the number of particles, the actual number that there are, like trillions of them, and divide it by Avogadro's number, which is, as you know, 6.02 times 10 to the 23rd. So I can just make a substitution and replace the number of moles instead as the actual number of particles divided by Avogadro's number. And then you'll have the gas constant R divided by Avogadro's number. We call that Boltzmann's constant. Boltzmann's constant here, K sub B, is just the gas constant divided by Avogadro's number, which is this tiny little number, like 10 to the minus 23rd. So this is the physicist version of it. We'll sometimes write the gas law this way. Whatever's more convenient. If you have a number of moles, use the chemist's version. If you have the number of particles directly, then we'll use that version. One of our goals is going to be to understand how engines work. To do that, we have to be able to combine the gas law with mechanical things like forces and energy. So this example is just a warm-up of that. We have a totally frictionless piston which traps some gas in the chamber. Important to notice that we're told that the piston's totally frictionless, not restricted in its motion in any way at all. Okay, so it slides totally freely. That's crucial because you see, if the piston was like clamped or stuck in place, then the gas could be absolutely pressurized to, 1,000,000 atmospheres, and there'd be no connection between the pressure of the gas and the external pressure, like the atmospheric pressure, for example. But with the friction, with the piston being totally free to move, what that means is the gas pressure, the bombardment of the gas on the inside of the chamber, is just supporting the external forces from the outside, which includes the air pressure, and also the piston itself has some weight to it. So the first question is the analysis model to describe the piston. All they mean is, I realize that this thing is in mechanical equilibrium, force balance situation. So that's how we'll model it, as a mechanical equilibrium. Write the force equation for the piston. Okay, again, the piston is in force equilibrium. The pressure force must balance whatever external forces are pushing down on the piston, which includes gravity and the atmospheric pressure. Don't forget, there's not only pressure in the gas, but there's also outside atmosphere air here, which supplies some atmospheric pressure, P0. Okay, so we want to write the force balance equation. It says that the upward force from the gas in the chamber, that's P times the area of the piston, minus the, so there's the downward forces. The atmospheric pressure pushes downwards with a force of P times area. And then there's minus mg from the weight of the piston. and those have to all be in balance. Note that this equation determines how big the gas pressure must be. With a frictionless, freely moving piston, the gas doesn't like have any choice of what pressure it has. It's the piston will drop down until the gas pressure matches the downward forces. Remember, the smaller the container is, the greater the pressure is. So the piston just drops naturally until the gas pressure is big enough. Okay, and then question C is to find the height of the piston. The piston drops until the pressure is just so. So what height is that? That's using now the ideal gas law. PV equals nRT. You see, I know how big the pressure has to be from the force balance. That determines how big the volume of gas must be, and that's closely related to the height. You see, in other words, on the left side here, the volume of the gas is just the area of the chamber multiplied by the height. It's a cylinder, so just area times height gives the volume. So in other words, I can solve for the height. The height is going to be nRT divided by the pressure times the area. And the pressure times the area I can read off from part B. It's just equal to the downward external forces, P0A minus mg. There we go. Notice it was easier, like I didn't just solve for P because actually P times A is what ended up in the answer. This problem we see, we've got a spring attached to the piston now, so we know we're in physics land now. But it's a red letter problem, but you know, it's really just similar to the previous one. It's just that now there's an extra force supplied by a spring that's attached. So in this problem, we start off with the gas in a certain volume, atmospheric pressure, and at near room temperature. Then it's warmed up to 250 degrees Celsius, and we have to figure out how high it's going to rise when it does that. We think of it just like the previous question. In the initial picture, the spring is totally loose, which means that the pressure of the gas here is just equal to the outside forces pushing down on it. In this case, by the way, we're told that the piston itself has negligible mass. So we're ignoring the weight of the piston in this case. So in the first picture, I'll just have that the pressure of the gas must be equal to the atmospheric pressure. That's it. The spring isn't doing anything and the weight of the piston is nothing. In the second picture, now, again, same idea. It's in equilibrium now, but with extra forces that are acting, an extra force from above from the spring. Now you've got not only atmospheric pressure pushing down on it like before, but there's an extra force from the spring that's compressed pushing down as well. Okay, so let's write down the mechanical equilibrium equation. In this case, I'll call it P prime, the new pressure that it reaches. So I'll have P prime times the area minus the atmospheric pressure force, P0 times area, and then minus the force of the spring, the downward force of the spring, that'll be minus K times H. I don't know H, and I don't know P. I don't know what the pressure is, but I'm gonna get another equation to work with from the ideal gas law. Okay, so that's how the pressure and the height are related. Also, they're related through the ideal gas law. Because I know no matter what the pressure of the gas is or what its temperature is, I know that PV equals nRT. So in this picture, in the second picture, I'll have P prime times V prime is equal to nRT prime. By the way, we can actually find the value of N, the number of moles, because we know the initial conditions of the gas. You can find the number of moles by taking the initial pressure times the initial volume over R times the initial temperature. Again, converting Celsius to Kelvin, that's about 293 Kelvin. The number of moles comes out to be about 0.2 moles. 0.208 is the number I have. Okay, so we actually know the number of moles. In this equation, this is actually an equation to solve for the height, because the pressure depends on the height. The higher it rises, that's when the spring is pushing harder, that depends on H. And of course, the volume depends on H as well. The temperature is known, so that's going to determine H. So let's see how it works when I plug in for P prime. P prime, in this case, I really have to divide by A. So P prime is equal to P naught plus KH over A. That's sort of like the pressure of the spring, so to speak. And then that multiplied by the new volume. The new volume is the old one plus A times H, plus the extra cylinder volume, V naught, plus A times H. And that is equal to nRT prime. This is an equation to solve for H. It'll have a positive solution for H when you plug in the new higher temperature, 250 Celsius. Of course, you got to convert to Kelvin, but plug in that new temperature and solve for H. There are two ways to do it. You do it analytically using the quadratic equation. That's one way to go. If you have the time, that's how you might want to do it. However, if it's an exam situation, then you need to know how to use your graphing calculator and solve for the value of H. I mean, it'll give a numerical number. Remember, you'll set y1 in your calculator equal to the left-hand side with all the numbers plugged in, and y2 will be equal to the right-hand side, and you'll find the intercept of the two graphs to figure out the value of H. Okay, so that's our solution to find the height H. Solve for H. And then in part B, what's the pressure of the gas? Well, that's easy. I already know that P prime is equal to atmospheric plus KH over A. So I would simply plug into that to find the value of P prime. Once you know H, then you know everything. In the previous question with the spring attached to the piston, the number of moles stayed constant from the initial state to the final state. We use the gas law at the initial state to find the number of moles, and then we use the ideal gas law again in the final state with the compressed spring to find the final pressure. Sometimes more than one thing stays constant. In that case, it was just the number of moles, but everything else changed: pressure, volume, temperature. Here we're pumping up a basketball. It's helpful to sketch the before and the after. We're focusing here on the air which goes into the ball, and I'm trying to figure out what initial volume of air was pumped into the ball. Okay, so I'm going to draw a sketch. Here at the beginning, here was the initial system of the air which is going to end up being pumped into the ball. It was just at atmospheric pressure, 1 atmosphere, and it had some volume, which I'm trying to figure out what it is. Okay, then that air gets squeezed down into the basketball. So now it's in the form of the air crammed into the ball. What I know here in the final state, I know what its pressure is. I know the value of P, or we called it P prime before. I know the pressure there, and I know it's a 10-inch diameter, so we basically know the volume of it as well. Knowing only the initial pressure and volume and the final pressure, how can I? Sorry, if I know the pressure and the volume, how can I use that to figure out what the initial volume must have been? That's the question. Okay. So there's there's a shortcut way to do it. The thing to notice, what you should always look for in these problems is what things stay constant. What stays constant between the initial picture and the final picture? Uh, N is constant. This cloud of air is exactly the amount of air that goes into the ball. So 1 mole here, 1 mole there, whatever it is. Also, I'm assuming the temperature stays constant. Like I didn't warm up the air as it went into the ball. I'm assuming it just stayed at room temperature. So also T stays constant in this process. Why does that matter? It's because PV equals nRT. So you see at the beginning I had P naught V naught is equal to nRT, number of moles that are in there, and the temperature, the room temperature. But that's exactly the same because N and T don't change. nRT is also equal to PV, the final values of pressure and volume. So you see, by recognizing what things stay constant, I can now relate the initial volume, which is what I want to solve for, V naught, to the other pressure, the other pressures and volume. In other words, V naught is just the final pressure over the initial pressure multiplied by the final volume. And I know all those things. I know that the pressure goes way up at the end, and I know the initial. I know the final volume of the basketball. Okay, so now it's plugging in. The final pressure. We're told that it's pumped up to a gauge pressure of 44.1 psi, pounds per square inch. Now, gauge pressure. Gauge pressure is not the actual pressure of the gas. Gauge pressure is what you measure using one of those tire gauges. They don't tell you what the actual pressure of the gas is. Really, what they tell you is the difference in pressure between the outside and the inside of the tire. In other words, gauge pressure, when you use a tire gauge, it's not really measuring P, the pressure of the tire. It's measuring the difference between the tire pressure and the atmospheric pressure. Why? Well, because it's just measuring the flow between the in and the out of the gauge. If they're equalized, the gauge is going to read 0. Does that mean the pressure of gas is 0? No, it means it's 1 atmosphere. So when they tell me that it's 44.1 psi on the gauge, what that really means is I have to add atmospheric pressure onto that to get the actual pressure. See, I'm solving for P. P is equal to gauge reading plus atmospheric pressure. So the pressure of the ball is not 44.1. The pressure of the ball is actually 58.8 psi. It started in the atmosphere at atmospheric pressure of 14.7. 14.7 psi is just the same as 1 atmosphere. Okay, I have to take that ratio multiplied by the final volume of the ball, which is it's a 10-inch diameter ball. So I have to multiply by the volume of it, which is 4/3 pi r cubed. The radius is 5 inches. Okay, so that'll give me the final volume. Last thing to say is notice how since I set up a ratio, I don't have to convert anything. I'd rather not have to convert psi to like pascals or something, and I don't have to. It's just a ratio here, so no conversion factors needed. If you don't set up this ratio, then what you end up doing is finding V naught as equal to nRT over the pressure, and then you waste a whole bunch of time doing conversions. This method saves you a lot of time. Follow it, set up a ratio to find the unknown quantities. In the filling the basketball problem, the number of moles and the temperature stayed constant as the basketball was pumped up. It was the pressure and the volume which changed. In the next question, we are warming up a hot air balloon, and we're going to figure out what temperature is needed until the balloon will take off. In the filling of a hot air balloon, the pressure and the volume stay constant. A hot air balloon doesn't change its volume as you heat it up. Keeps the same volume the entire time. What does change is just that you're warming the gas, and in the process of warming it up, some gas will escape the balloon. So in other words, in this problem, we have the pressure and the volume are constant. What is changing is that you start with some initial number of moles of gas and some initial temperature, which we're told is 10 Celsius. And then in the end, it's now been warmed up with a burner, and now it's at a higher temperature. But in the process, some gas had to escape. Otherwise, there'd be a higher pressure inside the balloon than outside. So now we've got some number of moles N and a higher temperature T. Of course, our job here is to figure out what the temperature must be afterwards. How can we find the temperature afterwards? Well, there has to be a certain number of moles of particles in the balloon so that it's buoyant enough to float. So first we'll look at ideal gas law, and then we'll look at buoyancy, and the combination of the two will let us find the temperature. So first in this problem, P and V stay constant. What this means is we've got P naught, V naught. That's equal to nRT initial. That's just gas law. However, PV is also equal to nRT final after it's been warmed. This lets me set up a simple ratio to find the final temperature. This tells me that the final temperature, it would be found by the initial number of moles divided by the final number of moles multiplied by the initial temperature. Now remember, there's actually more gas in there at the beginning when it's cold. When you warm it up, the gas is less dense inside, and so N naught is bigger than the final number of moles. So it's going to give us a higher temperature needed to make the balloon float. The question is, I don't know the number of moles. I need to figure out how much gas is going to be in there in order to make the thing float. Notice that the number of moles is proportional to the density of the gas. So it's going to be simpler to write N naught over N as the initial density divided by the final density. Okay, this doesn't tell me what, I still don't know what the densities are, but to do that, I'll have to use Newton's laws. So now I'll think about buoyancy. And on a hot air balloon, there are three forces that have to be balanced in order for the balloon to float. First, in order for it to float, I need, well, there are three forces. There's the buoyant force. There is the weight of the air. That's mg for the air. There's also the weight of the cargo, mg. Weight of the cargo we're given. Okay, so in order to float, of course, these have to be balanced. The buoyancy has to be big enough so that buoyancy minus m air g minus mg, the cargo weight, is equal to 0. Okay. How big is the buoyancy? The buoyant force depends on the weight of the displaced air. Now remember, the air outside the balloon is the cold air. So the weight of the displaced air depends on the cold air density. In other words, rho naught. Rho naught V, that's the mass of the displaced air times G. This is the weight of the air inside the balloon. That's the hot air when it's I want it to float. That's rho, just what I called rho V times G. And there's the weight of the cargo minus mg. Notice what this does. It tells me what the density of the air inside the balloon must be in order for it to float. It gives me a value of rho, which I have to plug in to find the temperature, which I'll do. It tells me the temperature is the original density, the cold air density, which is given, divided by rho naught minus m over v. That's the mass of the cargo divided by the volume of the balloon. It's that times the original temperature. All of which, actually, I should say, these are actually V naughts. It doesn't matter. It's the same V throughout the process. It's the same volume throughout. This gives me the final temperature, and this is T naught. Gives me a final temperature for me, which is 473 Kelvin. Remember, whenever you use ideal gas law, you have to plug in the temperatures in Kelvin. Then, if you wish, you can convert it back to Celsius. Here we've got two containers, A and B. They're initially at different pressures. Container A is at a much higher pressure than B. Their temperatures are different. The temperatures are maintained with heaters or something as you open the valve. So initially different pressures. That means when you open the valve, the side with higher pressure is going to win, and the gas will stream into B until the pressures equalize on both sides. So again, it's going to be combining ideal gas law with concepts of force equilibrium. In this case, it's just that the pressure on both sides has to balance in the end. So in the final state of things, we must have some final pressure in both containers. Let's call it PA prime. Prime in this case means the final value. It must be equal to PB prime. That's the final condition. That's really just mechanical equilibrium, balance of forces. Okay. Now our job is to actually figure out what that pressure is. The approach here is, I know the pressure of A at the beginning. I'd like to know what it is at the end, and then I know the pressure throughout. The idea is going to be, I'd like to know PA prime. I want to think in terms of ratios. I'd like to know PA prime over PA. If I can figure that out, then I'll know what the pressure is in the end. Well, the pressure in A at the beginning, let's think about what this is. Now let's put the ideal gas line. PV equals nRT. So this is equal to Na prime times R times the temperature. R will cancel in the ratio, so I'm going to leave it off. That's Ta prime divided by Va prime. That's just the numerator. All I've done is plug in the fact that P is equal to nRT over V. And likewise in the denominator, except it's the initial values, not the final ones. So that's NaTA divided by Va. Okay. Now, a lot of things in this ratio actually cancel, because you see container A maintains its temperature throughout, and its volume doesn't change. So the temperature part of the ratio just cancels, and so does the volume part of this ratio cancels off. So we learned that the change in the pressure is just equal to the change in the number of moles of gas in the container. It's Na prime over Na. Okay, so now we're getting somewhere. I don't know how many moles of gas there are in the two containers. However, we'll be able to figure it out based on what is given. So it kind of outlines the strategy here is, which I need to think in terms of the number of moles of gas to figure out what the pressure is going to be. Okay, so what do I know about the moles of gas in the container? Well, some of it is going to stream out of A into B. So A and B, they change. However, the total amount stays fixed. So crucial to keep in mind here that Na Na prime plus Nb prime, the total amount at the end is of course the same as it is at the beginning. Okay, this is a relationship between the number of moles A prime and number of moles A. The number at the end in A compared to what it is at the beginning. If I can just figure out how B prime and A prime relate to each other, I'll have the left side only in terms of A prime, and then if I can figure out how A and B are related at the beginning, the right side is only going to be in terms of A then, and we'll have our ratio that we want. So we'll come back to that. I need to figure out how A and B prime are related, the number of moles, okay, both at the end and at the beginning. Okay, so let's start with at the end. Let's see if I can figure out NB prime over A prime. So I'll plug in the gas law to do it. N is equal to PB prime, VB prime divided by TB prime. And then same thing for NA prime, that'll be PA prime, VA prime divided by TA prime. I just plugged in the gas law in the numerator and the denominator. And again, a lot of these things are going to cancel. Or maybe not cancel, but simplify. It'll all simplify down. You see, first of all, at the end, the pressures are equal in A and B. So PB over PA final is just equal to 1. So there's a number 1 in there from the pressure ratio. Then VB prime over VA prime. Well, the volumes I know. You see, it tells me container B has 4 times the volume of A. So I get a number 4 from VB over VA. Finally, this temperature ratio comes out to be TA prime over TB prime when I simplify the fraction. And I know that the temperatures stay fixed. TA stays at 300, while B stays at 400 throughout the process. So A over B is always 3/4. And that means in the final state, B has exactly 3 times the amount of gas as in A. That's at the end. The point of this is now I know that NB prime is 3 times A prime. And I could plug that in on the left side here for the total moles. And now I'll have an expression that involves only Na prime. Finally, I just need to do the same thing again for the initial number of moles. Can I figure out how NB compares to Na at the beginning? The answer is yes, just like I did here. Again, I'll have the ratio of the pressures. Now it's the pressures at the beginning. Now at the beginning, the pressures were 5 times 10 to the 5th and 1 times 10 to the 5th. That means PB prime over A prime is equal to 1/5. What about the volume ratio? Well, that doesn't change. That stays at 4. Container B is 4 times as big as A. And again, the temperatures don't change either. It still stays at a ratio of 3/4. So that means the number of moles in B compared to A at the beginning is equal to 3/5. And now we're set. Now I can plug both of these into the total number of moles expression here. and I'll know how the number of moles in just container A will change. That tells me the pressure. Okay, so let's plug these things in. Na prime plus Nb prime, but Nb prime is 3 times Na prime. So I'll have, that means I have Na prime 1 plus B over A prime, which is 3. And on the right side, I'll factor out Na, and that gives me 1 plus B over A, which is 3/5. And this, when I simplify it, it's going to tell me that Na prime, so the point is, I already know that Pa prime over A is the same as the mole ratio. So the change in pressure in container A is just the same as the change in the number of moles in container A, which now I have that ratio. Na prime over Na is equal to, this is 8/5 divided by 4, which is 2/5. In other words, the final pressure is 2/5 of what it was at the beginning, which means it's 2 pascals. Finally, the final pressure, it's actually the same in A and B, comes out to be 2 times 10 to the 5th pascals.